one of the central concepts of elementary geometry that we're familiar with is that of area. We've spent a lot of time, most of us, memorizing the area formulas for triangles and circles and rectangles and so on and so forth. We're going to now look at area from our axiomatic perspective, and it's going to turn out that we've actually shown already many of the things that we need to see that area is well defined, behaves the way that we're familiar with, and so forth and so on. There is going to be one major wrinkle that we're going to have to encounter that will show how dealing with things rigorously can sort of illustrate what's behind the scenes in a lot of the things that we're familiar with. So, in order to talk about area, we need to talk about regions, two-dimensional, basically, regions in the plane, which we've only talked a little bit about so far. So we're going to start with some terminology. A triangular region. A triangular region T is the union of a triangle, which I'll denote triangle ABC, with its interior. So the picture that we have here is of a triangle ABC, and then we're also considering the interior of it. So all these things together making up this sort of two-dimensional region here is what we're going to call a triangular region. Given a triangular region T, or given this triangular region T, I should say, the boundary of T is denoted the boundary of T. So this is a cursive lowercase delta, basically, and it's used in many disciplines for the boundary of an object or whatever. And it is the triangle ABC, so the region, but only the outside border of the region. This is what we call a triangular region. What we're going to do is we're going to talk about the area of more general regions by recognizing them as unions of these triangular regions. The idea basically is that if we have some polygonal region like this, then we can split it up into triangles like this and see the polygonal region involved as a union of a bunch of triangular regions. So we take, we're going to use that for our for the next part of our definition. A polygonal region is a union of triangular regions. So it'll be something like T1 union T2 union T3, etc., up through up through a Tn. Triangular regions, all coplanar, of course. Our polygonal regions need to lie in a single plane, where for any Ti and Tj, the intersection of the two Ti's and Tj's is either empty, a shared vertex, or a shared edge. So, for instance, in this polygonal region that we've got here, we have that two of the triangles share an edge here. And then we've got a point here where if we take, say, the top triangle and the bottom triangle, their intersection is simply this point, the shared vertex between them. Or we could look at triangles like this one over on the right and this one over on the left, where their intersection is empty. The point to this condition here is that you don't have any overlap. None of the triangular regions overlap one another. They only meet each other in shared edges or vertices. Now, for a given polygonal region, there might be more than one way of expressing it as a union of triangular regions. So let's consider the same polygonal region here. So let me take that region, and then let me go ahead and copy it over here. Now, both of these are polygonal regions, we can see, because, for instance, we could write the left one as a union of triangular regions like this, but we could also set it up as a union of a lot more triangular regions, say like this. And so these are two different potential triangularizations of the same region. So for a polygonal region R, if T1 through Tn are some triangular regions, and R is the union of T1, T2, union Tn, where the Ti intersect Tj are, as before, empty shared edge or shared vertex, then we say that this T1 union T2 up through Tn is a triangularization of R. And the point is that a single region R can have, and does have, many different triangularizations. So for instance, we could have the triangularization over here with T1 and T2, or we could have the one over on the right with, let me call it T prime 1, T prime 2, T prime 3, T prime 4, T prime 5, and T prime 6. And in fact, the recognizing that a single polygonal region can have multiple different triangularizations is actually key to where some of the care needs to be taken when we go to try to define the area of the region R. Now, we can also talk about the boundary of R. And the boundary of R is a lot easier to intuitively grasp than it is to precisely define. So the boundary of R is the set of all points, A belonging to R, such that there exists a point B in the plane of R such that the segment AB, except for A, intersect R is empty. So how does this work? So if I look at my region R and I look at my left figure up here, then if I take a point A right there, and then I draw any segment, or it's possible for me to draw a segment that goes over here to a point B, And the only point of this segment AB that actually lies in R is the point A itself. No other points of this segment actually lie in R. So this tells me that A is on the boundary of R. On the other hand, if I took a point C here, this point C is not in the boundary of R, because no matter where I draw a segment with C as one of its endpoints, it's going to include some points that are in the region R other than C. And so C isn't on the boundary. So A is on the boundary of R, C is not on the boundary of R on the sketch above. We denote the boundary of R by the boundary of R using the same notation that we used for the boundary of the triangular regions before. Now, the boundary of a region can be used to describe essentially the shape of that region. If we look at the boundary of R, the specific R that we have on the screen up above, the boundary is are given by the white segments, and we can see that it appears to be a trapezoid. We would call this, therefore, a trapezoidal polygonal region. So if the boundary of R is a triangle, we say that R is a triangular polygonal region. And similarly for trapezoids, rectangles, etc. We could talk about square polygonal regions, rhombus polygonal regions, parallelogram polygonal regions, etc. So we can describe a polygonal region by the shape of its boundary, if its boundary is itself a polygon. Now, note that not every polygonal region will, in fact, be one of these. So, for instance, the following is a polygonal region. And we can show this simply by exhibiting a triangularization of it. Because we can split this region up into a bunch of triangles, we can see that this sort of donut shape is a polygonal region, but in this case its boundary consists of both the outside polygon, which looks to be a hexagon, and the inside polygon, which is a pentagon. So we would not, in fact, use any sort of name for this polygonal region. We would not say that this is a hexagonal polygonal region or a pentagonal polygonal region or anything like that. It is a polygonal region because it's built up out of the union of triangular regions, but we wouldn't give any sort of name to it. Also, note that circles are not polygonal regions under this definition. The only polygonal regions for us have to be a union of a finite number of triangular regions, and you cannot describe a circle using a finite union of triangular regions. Okay, so given all of this this notation and definition, we can define what an area function ought to be. Now, one thing that's nice about what we've done so far is that we don't have to use an axiom here. Now, when we wanted to talk about a distance on a geometry, we had to introduce an axiom that allowed us to do that, an axiom that told us that a distance function existed. When we wanted to do angle measure, we needed an axiom for that. And so these various measures that we've been working with, we needed to have an axiom. However, it turns out that we don't need it. What we're going to be able to, for area, we're going to be able to define the sort of properties that we would want an area function to have, and then prove that we can actually construct one. Prove that there, in fact, is an area function that does everything we want it to. So let's go to definition 92. An area on a geometry is a function alpha satisfying the following conditions, A1 through A4. All right, and here we go. First, condition A1 is that alpha is a function from curly r to r, where curly r, let me make that look a little bit different, where R is the set of polygonal regions in our geometry G. So the area function is going to take as an input a polygonal region and give as an output some number. This is going to be the area of that polygonal region. So part 2, for any polygonal region R in our geometry, we have to have that alpha R is positive. We don't want to consider zero area or negative area regions. We want to keep ourselves solidly in what makes intuitive sense to us in terms of area. Any polygonal region has to have positive area. A3, we want to make sure that our area is consistent throughout our geometry, that we don't have weird stretching of space where things are arbitrarily bigger in one place than another. So we want to show that if two triangles are congruent, their regions have equal area. And then finally, A4, if R1 and R2 are two regions, and R1 intersect R2 is only contains edges or vertices, that is, there's no actual overlap between the two regions, then the area of R1 union R2 should be the area of R1 plus the area of R2. So if I've got two different regions that don't overlap at all or only overlap in segments and points, then the area of the whole should be equal to the area of the pieces. So these are the sort of basic conditions that we would want out of an area. Any function that makes sense to us as an area function ought to satisfy these conditions A1 through A4. And it turns out that the last theorem that we proved the last time will allow us to show that we can, in fact, define a function that does this. So let's recall the following. Theorem 91 says that given triangle ABC, the product of an altitude, or the length of an altitude, with its corresponding base is constant. In other words, if I look at the three different altitudes of this triangle with their three different corresponding bases, and I multiply their lengths together, I always get the same number. That means that that number is something that can be uniquely and in a well-defined way associated to the triangle ABC. So let's use this in order to build an area function. So from this, we can start building, or we can build an area function. Because all of our polygonal regions are built up out of triangles, if we can define an area function on triangles, we can use that in order to define an area function on arbitrary polygonal regions. So, given a triangular region T, let's sketch out what the situation is here. Given a triangular region T, we have that the boundary of T is, by definition, a triangle. And in this triangle, we can let the boundary of T be given as triangle ABC. And we can let, let's say, D be the base of the altitude at A. So in other words, we can take a line segment from A over to the line BC that is perpendicular there, and we can call this D right here. Let's define the area of T to be the number AD times the number BC. Now, we're actually going to adjust this a little bit for a second, but let's start here. Now, the reason why Theorem 91 helps us is because if we're just given a random triangular region T, then that defines three vertices, but there's no particular reason to pick any one of those vertices as special over any of the others. And so by labeling the vertices A, B, C, and specifically choosing, let D be the base of the altitude at A, if we didn't have Theorem 91, then we would have to ask, all right, well, what happens if we labeled the vertices some other way? What happens if we switch the labels of A and B? What Theorem 91 tells us is that at the end of the day, switching any of the labels of the vertices doesn't change this number. This number here is independent of the labeling of A, B, and C. And so in fact, this is a well-defined number given just the triangular region T without specifying ahead of time what the vertices are or some special order for the vertices. So this means that we can associate a number to a triangular region in a well-defined way. Now, in order to make the area function work the way that we expect it to, we're actually going to include a factor of 1/2 here. We'll see why we want to do that in a little bit. This 1/2 makes the area function we're looking at behave very much in the way that we expect. However, it turns out that the The area function would work perfectly well if you didn't include this 1/2. It would still be, we would still be able to use it to build a an area function on for our geometry. Okay, so this works perfectly well to give us a well-defined area for a triangular region. But what about a polygonal region? Let's ask about that. Let's say that we've got some polygonal region that looks like this, maybe. And we want to say, all right, well, how do we find the area of this? How do we define the area of a region like this? Well, the one thing we know about polygonal regions is that they can be written as the union of triangular regions. Every polygonal region, by definition, has a triangularization. So R has at least one triangularization, where R is the union of T1, union T2, etc., union Tn for some n. So here's an example. Now you do have to be a little bit careful with the triangularization here. Currently what I have written is not technically a triangularization because this point right here is a vertex of some of the triangles that include that point, but not all of them. This big triangle right here doesn't include that point as a vertex. We can fix that, though, simply by introducing another triangle that goes like that. So this is a proper triangularization of R. And we could label our triangles if we wanted to. So here's a triangularization of R with 7 triangles. So we know that what we want out of our area function is for the area of a region, or if I've got 2 regions that don't overlap each other, maybe they meet each other at edges and vertices, but they don't overlap, then the area of the whole should be the sum of the areas. So why don't we just define the area of R to be the sum of the areas of the triangular regions? So we could define the area of R to be the area of the sums of the areas of the triangular regions inside. And this is what makes the most sense to us. It turns out that this works, but we actually have quite a lot of work to do to show that it works. But this is the idea. So let's write down our theorem. Our theorem basically states that alpha, as we have defined it, is an area function, as per definition 92. Oh, this theorem has a number. This is theorem 93, of course. So in particular, it satisfies the 4 axioms that we had before. So let's see how that goes. It turns out that the difficult part of showing that alpha satisfies A1 through A4 comes actually right at the beginning. So remember that the first condition, A1, we needed to show that alpha is a function from the set of polygonal regions to the set of real numbers. And it looks like we've got that, but there's a well-definedness issue. And the well-definedness issue is that we can have more than one triangularization of the same region. So for instance, if I take the same region R up here, but I start triangularizing things using these red triangles, the red triangles give another triangularization of R that doesn't necessarily have anything to do with the original triangularization. So if I've got two different triangularizations of my region R, how do I know that this number is the same for the two different triangularizations? That actually takes quite a bit of work, and we're going to run through the arguments or sketch. We're going to talk about some of the arguments we're going to make that one would use to make that. We're not going to go through them in full detail because, as it turns out, they're fairly complex. However, you can check the notes for a what should be a complete treatment of this question. However, let's leave that for the moment. Let's assume that this way of defining area for a polygonal region does in fact work, does in fact give us a function, and let's see how we can use that to prove that the other axioms, or conditions rather, hold. A2 through A4. So, assuming A1, which we'll come back to, let's show A2 through A4. So A2 said that for any region, we have that the area of the region is positive. So for that, we note that for any triangular region, T, we have that the area of T is 1/2 times BH, where B is the length of a base of the boundary of T, and H is the corresponding altitude, or the length of the corresponding altitude. So we have that the area of T is positive. 1/2 times base times height. Both B and H are positive numbers, and therefore the area of T is positive. So if T1 union T2 up through Tn is a triangularization of R, then the area of R is equal to the sum of the areas of the TIs, but each of the area of the TIs is positive, and therefore the sum is positive. So the area of any polygonal region is positive. A3 says that if two triangles are congruent, then their areas are the same. The area of the regions with those boundaries are the same. So let's let T1 and T2 be triangular regions, and let's suppose that the boundary of T1 is congruent to the boundary of T2. Let's actually be more precise than that. Let's say that the boundary of T1 is actually equal to triangle ABC, which is congruent to triangle DEF, which is the boundary of T2. So we've got A, B, C, D, E, F. Now, let's let D be the base of the altitude from A. Oh, sorry, not D. We already used D. We want to let G be the base of the altitude from A, and H the base of the altitude from D. So we've got things that look basically like this. So now, pardon me. So now we can say by angle, side, the triangle ABG is congruent to the triangle DEH. Because the angles at B, the angle at B and the angle at E are congruent. And then, of course, the angles at G and the angle at H are both right angles, hence they're congruent. And the side length AB is congruent to the side length DE, and so we have angle, side showing these are congruent. So, in particular, that means that the segment AG is congruent to the segment DH. Therefore, we have that the area of T1, which is equal to 1/2 times AG times BC, is equal to 1/2 times, now AG is congruent to DH. So the distance AG is equal to the distance DH. We also know that the segment BC is congruent to the segment EF. And by definition, 1/2 times DH times EF is the area of T2. So this shows that if two triangular regions have congruent boundaries, then they have the same area. So that handles A3. And now let's handle what happens when we have two regions that only overlap in vertices or edges. So now, let's let R1 and R2 be polygonal regions. Therefore, we can say, let's let T1 union T2 union up through Tm be a triangularization of R1. And let's let R2 being, we'll do U1 union U2 up through UN be a triangularization of R2. So the picture that we want to have in mind is something like the following. We have a polygonal region R1 here, a polygonal region R2 here. And we want to show that the area of the whole region is equal to the sum of the areas of each one. So we can assume that R1 has a triangularization. Maybe it looks something like this. And just throwing sort of random triangles in here. So there's a potential triangularization of R1, and then R2 might have a triangularization that looks like the following. So our first impulse would be to say that we can use the triangles from R1 and R2 to get a triangularization of the union R1 and R2. And we almost can. We need to be a little bit careful here. And that's because, at least in the way that I've sketched it out here, this is not technically a triangularization of R1 and R2. And the reason for that is that the triangles T9 and U2 do not intersect in a shared edge or vertex. The intersection of T9 and U2 is this segment that I've got in yellow, which doesn't really show up. Let me make that clearer. This green segment is the intersection of T9 and U2. And while that is a side, an edge of T9, it's not an edge of U2. However, we can fix this. We can refine the triangularization of R2 by introducing a new line to it that goes like this. And now we can split the original triangle U2 into a couple more, which we'll call maybe U6 and U7. So going through this process of refining the triangularization by introducing new line segments which give new triangles that build up R2 is what we'll do in order to take two triangularizations of R1 and R2 and turn it into a triangularization of their union. All right. So by refining the triangularizations of R1 and R2, we can make the union T1, union T2, union up through Tm, union U1, union U2, up through Un, a triangularization of R1 union R2. The fact that R1 and R2 only intersect in line segments and vertices is what allows us to go through this process. And so we can get a triangularization of R1 union R2. Therefore, the area, let me try and get this on one line. The area of R1 union R2 will be the sum of the areas of the TI plus the sum of the areas of the UIs. But we know by definition that the sum of the areas of the TIs is exactly the area of R1, and the sums of the areas of the UIs is precisely the area of R2. So that shows us that the area function satisfies the condition A4 that if I've got two regions that only overlap in segments or vertices, then the area of the whole is the same as the sums of the areas of the parts. All right, now let's see what some of the consequences of this are. We're going to come back to the question of well-definedness in a second. But let's look at some of the consequences. And one of them is what many authors include as condition A5. One can just use an axiom to assert that there exists some area function. We don't have to, because we've proven that we can build it up. Or we haven't yet, but we can prove that we can build it up using this formula of 1/2 base times height for triangles. But many authors include A5, which says that the area of a square with side length 1 is 1. So we are going to be able to just prove this using our formulas, but this is why we introduced a factor of 1/2 into the area function. If we didn't have that factor of 1/2, if it were any other positive number, then A5 would not hold. All the other axioms would, but A5 wouldn't. A5 is sort of the statement here that completely normalizes our area function. It's very much like the axiom that we had about the sums of the measures of two supplementary angles being 180. It's a standardizing factor, a normalizing factor. So let's prove this, and the proof for this is in the same line of reasoning as we can use to prove the rest of the ordinary formulas for the areas of a parallelogram. Or polygon, sorry. Parallelogram is one of them, but not the only one. All right, so let's go ahead and take this, and let's assume that we know that the side length of this square is 1. So we can say, let quadrilateral ABCD be a square with the segment A with the distance AB being 1, and hence we get from that BC and CD and AD are also all equal to 1. And that's because we know that a square is a parallelogram, and so a parallelogram and a rhombus, which means that all of its side lengths are equal to one another. Now, if we want to know the area of a region like like the region ABCD, we can get that by splitting it up into triangular regions. So we can let T1 be the region with boundary the triangle of ABC, and T2 the region with boundary the triangle ACD. So now by I should have specified let R be the square polygonal region with boundary the square ABCD. So now we have that the area, we have that R is the union of T1 and T2, and that's a triangularization of R. So that means that the area of R is, by definition, the area of T1 plus the area of T2. Now, the area of T1 can be obtained by taking 1/2 times a base and an altitude of this triangle ABC. Now, because ABC is a right triangle, we can actually take BC as the base and take BA as the altitude, or indeed vice versa. So the area of T1 is 1/2 times the area of AB times the area of BC. And we have that the area of T2 similarly is 1/2 times the area of AD times the area of CD. Not the area, sorry, the length of CD. But we know that all of these lengths are just 1. So we get that the area of R is 1/2 plus 1/2, which is 1. So this condition A5 tells us that the area of a region can match sort of our intuition. One of the ways that we first learn about area is by looking at a region and saying, okay, how many unit squares would it take to cover this whole region? And that's basically assigning an area of 1 to a unit square. What condition A5 tells us is that the area function that we've defined has that property, has the property that a square with side length 1 has area 1, and so our intuition matches there. We can go on from this and use similar reasoning to prove the normal area formulas for various geometric regions, or polygonal regions, I should say. So, for instance, we can look at Theorem 94. So let's let quadrilateral ABCD be a quadrilateral. If quadrilateral ABCD is a trapezoid with line AD parallel to the line BC, and H is the height of the trapezoid, that is, H is the distance, is the shortest distance from A to the line BC. Then the area of the quadrilateral ABCD is equal to 1/2 times the height times the length AD plus the length BC. The proof of this is sort of similar to what we used for the square. So what we'll have is some picture like the following, where we've got A, B, C, D, some trapezoid like this. And when we set it up this way, then H is the this distance here, the shortest distance from A, from the point A up to the line BC, which forms this sort of altitude here, which is not being used for no reason. And so if we want to know the area of this trapezoidal region, then we figure it out by splitting it up into triangles. And this trapezoidal region can now have its area computed as the area of this triangle plus the area of this triangle. And when you work out what that looks like, then you get exactly the formula here. So the area of a trapezoid is 1/2 times the height times the sum of the upper and lower bases. All right. Similarly, if quadrilateral ABCD is a parallelogram, then the area of quadrilateral ABCD is equals H times AD, where H is as before. Now, this is going to be an exercise to prove this, and the hint is that every parallelogram is already a trapezoid. So you can go ahead and use part 1 of Theorem 94, once you have it, in order to prove part 2. And then, if quadrilateral ABCD is a rectangle, then the area of ABCD is equal to the length AB times the length BC. And the hint here is that every rectangle is a parallelogram, so you can in fact use part 2 in order to prove part 3. All right, and then the last application that we have of our theory of area for now is Theorem 95, which tells us about the areas of similar triangles and how they interact with each other. It tells us that if triangle ABC is similar to triangle DEF, then the area of triangle ABC divided by the area of triangle DEF is equal to, now whenever we have a similar triangle, we have a certain constant of proportionality involved. To say that triangle ABC is similar to triangle DEF means that there's a certain ratio that we get when we take corresponding lengths. So when we look at this triangle, we know that AB over DE is equal to, for instance, AC over DF, which is BC over EF. And so there's this single number which sort of measures the similarity between the two. If the number is large, then that means that triangle ABC is a scaled up version of triangle DEF. If it's small, that means it's a scaled down version. And when you look at various lengths on these two triangles, for instance, corresponding altitudes, then the ratio of corresponding altitudes is equal to this constant of proportionality that you get between the two triangles. However, when we look at area, the ratio of the areas is not exactly equal to the ratio of the lengths. Instead, it's the square of it. One way of intuiting what's going on here is that area is essentially a two-dimensional measurement, whereas similarity says that the one-dimensional measurements between the two triangles are all sit in the same proportion with one another. And so as we move from a statement about one-dimensional measurements, the side lengths, up to a statement about two-dimensional measurements, the areas, then the ratios change by essentially squaring them. Proving this is really a matter of just looking at the formulas for the areas of the two triangles. So we know that the area of triangle ABC is equal to 1/2 times I'll call it B1 and H1 for a base and height of the first triangle, ABC. And the area of triangle DEF is 1/2 times B2 times H2. So the 1/2s will cancel, of course, and then B1 over B2, this is a ratio of two corresponding sides. When we go to write down our areas, we can choose to use corresponding bases here. Bases, so that B1 over B2 is in fact the same as AB over DE. In fact, we could just go ahead and use the length AB for B1 and the length DE for B2. But from there, we have a ratio of corresponding altitudes, and an exercise that we've had, or a theorem that we've had, says that the ratio of corresponding altitudes is equal, again, to the same ratio. The ratio of corresponding altitudes in a triangle is equal to the ratio of the corresponding sides. And therefore, we have that this is just AB over DE squared. So in other words, if you've got two similar triangles, but one of them is twice as big as the other one, then it will have 4 times the area. If it's 1/3 the size of the other one, it'll have 1/9 the area, where size is being measured in terms of the side lengths, this ratio of similarity between them. All right, there's our applications of area. Let's come back and consider the question of well-definedness. Let's take a region here. I'm going to make it sort of big because I want to illustrate what's going on. It turns out that the process for proving that that two triangularizations give the same thing can be complicated. So let's go ahead and take the following triangularization. So there's one triangularization of the region R. And let's take another triangularization. Let's take the one that goes up here. We'll go like that, like that, like that, like that, and like that. So we have two different triangularizations here. We've got the blue triangularization, which writes R down as a union of 4 triangles. We have the red triangularization, which writes it down as a union of 6 red triangles. And the question is, how in the world are we going to be able to make sure that if we take the sums of the areas of the blue triangles, that we get the same thing as the sum of the areas of the red triangles, without assuming that we have an area function in place already? Well, it turns out that the approach to it follows the following strategy. What we're going to do is create a triangularization of R that's a refinement of both of the triangularizations that we have. We're going to create a new one. And we're going to do that in the following way. We're going to start drawing some horizontal lines. And we're going to draw these lines in such a way that they intersect any point on the graph. Any point on the graph that is an intersection of any of the lines that are contained in one triangularization or the other. So we've got a whole bunch of parallel lines here. And so we're going to throw a bunch of these in. Now, what happens is we're going to look at each one of these sort of horizontal strips. And for each one of these strips, that's bounded on the left and the right by the sides of R, we're going to look at the region that's being given there. And for each one of these horizontal strips, we might have a triangularization already, and we might not. So for instance, in the bottommost strip, which I'll call R1, then you can see that all of the region that lies in this first strip, R1, altogether forms a trapezoidal region. And it's got some red and some blue segments in it that are dividing that region into a number of triangles. So the region R1 that lies between the bottom two yellow lines is already triangularized. But then we've got the region R2, which lies between the second and third yellow lines from the bottom. And we again have a trapezoid that's given by the region R that lies between the two lines at the edges of R2. But now the red and the blue lines haven't turned it into a triangularization yet, so we need to add some new ones. So we're going to add in even more lines. And we'll continue doing this up. And so I noticed already that I need to put in even another one because I need to include all of the vertices of R, as well as all the vertices of the triangles and the triangularizations, and in any of their intersections. All right, so looking at R3, I can see that I've got some trapezoids that I need to turn into triangles, a union of two triangles. So we might do it like that. R4 has some also. Now, the process that I'm doing is highly non-unique. There are lots and lots of different ways that you could do this, that you could create a triangularization that basically encompasses all the information, all the lines that are involved in both the red and the blue triangularizations that we started with. And any one of them will do. So now, at this point, assuming there's another one, there's another one, there's one. So now, one more. And another. So now, assuming that I haven't missed any, we now have the region R broken up into a bunch of triangles. And we've got it split up in terms of these strips, these R1 through R7. And each one of those strips is broken up into a bunch of triangles. And so what we have is a great big triangularization of the whole region R. And what we're going to do, or what we have to do in order to show that the area function is well defined, is basically to show that it's well defined on each of these strips. What we show is that the area function alpha is well defined along each strip R1. So in other words, we show that if we have a trapezoidal region where the triangularization only involves segments that go from the bottom of the trapezoid to the top of the trapezoid and no other messiness in between, then the area is well defined. So what we want to do is we want to show that if we've got some random thing like this, and then we take any random triangularization, then we always get the same value out of it. And basically what we do is we show in this special case, for this special kind of triangularization, that the area of this triangularization is equal to actually the formula that we had before. 1/2 times the height times B1 plus B2, where B1 and B2 are the lengths of the top and bottom, and then H is the height of the trapezoid. But the point of this is to show that this doesn't depend on the triangularization. What you do is you show that the sum of the areas of these three triangular regions is always equal to this expression over here, which only depends on B1, B2, and H, and not the specific makeup, size, or anything of T1, T2, and T3. And basically what that shows is that the area of this region R1 is well defined because it is being split up into triangles in this form, where all the triangles are all the segments are going from the bottom of the trapezoid up to the top. And this also shows that the area inside R2 is well defined, the area inside R3 is well defined, and so forth and so on, all the way up. And so now what we have is that this shows that if we add up all of the little tiny triangles that we have in our refined triangularization, we've got 1 million tiny little triangles in here, then we get a certain number, and it doesn't depend on how we group them up. And so basically what happens next is that we label all these triangles T11, T12, T13, T14, T15, T21, T22, etc., etc., and we label all the triangles in our big decomposition here. And so essentially what we show is that the area of R is equal to the sum of all the Tij's, all the little Ti's inside here. But the point is that's equal to the sum of all the Tij's, where Tij is in a red triangle, or where we group them up according to their according to the red triangles in the decomposition. Let me state that a little bit better. The point is that we can write this as the area of the Tij in the first red triangle plus the sum of the Tij's that are in the second red triangle, and so forth and so on, where we get all the ones in the last red triangle. And so by doing that, we see that this is the area of the first red triangle plus the area of the second red triangle up through the area of the last red triangle. And so we show that, that the area of R is this. But the point is that we can also group them up according to the blue triangles. We can group up all the little tiny Tijs so that we gather all of the ones in the first blue triangle together, all the ones in the second blue triangle together, so forth and so on. And so we can also get that this is equal to the area of the first blue plus the area of the second blue plus the area of the last blue triangle as well. And so what this shows is that if we add up the areas of all the red triangles, we'll get a number, and that's the same number as we get when we add up the areas of all the blue triangles, and that's because they're both equal to the sums of the areas of a whole bunch of tiny little triangles in our region. There's a lot more detail that goes into it if one wants to be really, really precise about it. I highly encourage you to read through the notes carefully to see how that goes. Fortunately, we only have to do this once, and then we can use the area function as much as we like in order to solve all of our geometric problems.